What I have here are three lengths of paper that are all different lengths. And what I've done is I've taken those three and put them into a triangle. And in this triangle, the white one is the same length as the white one there. The red one here is the same length as that red one. And the green one is the same length as that green one. And I put them together into this triangle right here. So my question then is, can I take these three lengths and make a different triangle? Or if I put these three lengths together, will I always get this exact same triangle? Or could I get a different one? Well, let's maybe try it. Let's see if I can maybe put these together in a different way. Okay, so I've just put them together and matched them up, and you can see that I get the exact same triangle. Well, could I maybe, if I take, say I try to make this angle a little bit bigger, so I could maybe widen that angle a little bit. Well, now those sides don't match up. Maybe if I try to make this angle a little bit bigger, well, then those sides don't match up. And so any way that I try to move this away from this triangle right here is going to make it not be a triangle anymore. So there is no different triangle that I could make. So if these are the three side lengths I have, this is the only triangle that it's possible to make with those three side lengths. So what this tells us is that if we have two different triangles, where the corresponding sides are congruent to each other, then those triangles must be the same triangle. So we actually don't even need to look at the angles. So in the last lesson, when we were looking at congruent triangles, we had to show that every single side was the same as every single other corresponding side, and that also all of the corresponding angles were the same. Well, we can take some shortcuts, and that's what this lesson is about. So we have a side-side-side postulate, congruence postulate, which says that if the three sides, so that's the side, side, and side, the three sides, the corresponding sides, if those are congruent to each other, that is enough to say that the two triangles are congruent. So we actually don't even need to look at the angles. If we know that the three sets of corresponding sides are congruent, that's enough to tell us that the triangles must be congruent. The angles are forced to be the same if that is the case. So if we have, so these three statements here just tell us that the three sets of corresponding sides are in fact congruent to each other. And so if we have that the three sets of sides are congruent to each other, then we can say that the triangles really are the same triangle. So we can say that triangle ABC is congruent to triangle RST. Now in example 1, we're going to use the side-side-side congruence postulate to prove that two triangles are congruent. So again, in the last lesson when we were looking at trying to show that two triangles were congruent, we had to show that every set of corresponding sides was congruent and that every set of corresponding angles was congruent. But in this lesson, we're going to take that shortcut, the side-side-side congruence postulate, to show that these two triangles are congruent. So what we're going to do first is just write out our givens. So we were given these two statements. So one of those is that segment KL is congruent to, segment NL. That's going to be this one and this one. Those two are congruent to each other. They're already marked on the picture. And the reason I know that that's true, again, is that it was given to me. Then I can also say that segment KM is congruent to segment NM, and that was also given to me. So that's the reason I know it's true. Now we could have, if you wanted to, join these together into one statement and then just written given as the one reason for both, or we can write it out as two separate steps. Either way, it doesn't really matter. All right, then what we always want to end with when we're proving something is the statement that we are trying to prove. So we're trying to prove that these two triangles are congruent, so I'm going to write that down as my last step. Now I don't know the reason for this yet, so let's get to that right now. So if we're trying to prove that this triangle is congruent to this triangle, and we're trying to do it by side-side-side congruence, then what we need to know is that all three corresponding pieces are congruent to each other. Well, we already know that this is congruent to this, and we already know that this is congruent to this, so then we need the third side, and that's going to be LM here. And LM is shared between the two triangles. That segment is a part of both triangles. And so I've been telling you that we'll get into the reflexive property. We'll get to use that in proofs. So this is why it's important to talk about the reflexive property as an actual thing rather than, because it seems obvious, it seems like it's a rather trivial thing to say, but this is why we need it. So we need to say that LM is congruent to itself because it's shared between the two triangles. So we can say LM is congruent to LM, and that gives us the third side that we need, the third set of sides. So we had this set of sides, we had this set of sides. Then to get the third side congruent, we need to state that LM is congruent to itself, and that's by the reflexive property. And now we have three sets of congruent sides, so we can use the side-side-side postulate to say that these two triangles are congruent. And we can just abbreviate it SSS. I'm fine with that as being the abbreviation for that. All right, let's look at example 2, letter A. So it says that triangle DFG is congruent to triangle HJK. So we're supposed to determine whether or not this is true. Well, we've got this set of sides congruent, we've got this set of sides congruent, and we've got this set of sides congruent. So yes, they are congruent, and we know that they have to be congruent by this postulate, the side-side-side congruence postulate. Part B. Okay, so if we look at, say, AD and BC, these are both 7, so that means these are congruent to each other. They share side AC, and so by the reflexive property, that's congruent to itself. But then if we look at AB and DC, well, this one's 3 and this one's 4. Those are not congruent to each other. So these two triangles are not the same, so this is false. And the reason that this is false is because AB, segment AB, is not congruent. So I'm going to draw a congruent sign with a slash through it. That means not congruent. It is not congruent to segment DC. Then for this one, let's look at triangle QPT is congruent to triangle RTS. Now actually this one is a little bit trickier. So the triangles themselves are actually congruent, but this statement is actually wrong. And we didn't really look in particular in the statement to this one because I wanted to wait till we got to part C for this. But if we look at this statement is incorrect. So even though the triangles are congruent, because we've got this set of sides congruent, this set of sides congruent, and then this set of sides congruent, the statement is wrong. So if we look at, say, okay, Q goes with R, and then T obviously goes with itself, and then P goes with S. So this statement is QPT. That's the order it's in. So it's circle, triangle, square. And this one is RTS. So that is circle, square, triangle. They're listed in the wrong order. And so this statement is incorrect. So the triangles are correct, but the statement is wrong. Example 3. Which coordinates of the vertices of the triangle are, give a triangle that is congruent to triangle PQR? Well, if we need to know congruence, we need to know the side lengths. So let's figure out the side lengths. So QR is 1, 2, 3 units long. PQ is 1, 2, 3, 4 units long. And then to find this third side, let's call it C for a moment. Well, this is a right triangle here, and so we can use the Pythagorean theorem. So 3 squared plus 4 squared is going to be equal to the third side, C squared. 3 squared is 9. 4 squared is 16. 9 plus 16 is 25. And then we can take the square root of both sides to get C. Square root of 25 is 5. So C then is equal to 5. Okay, so we need to find vertices that have these three side lengths, 3, 4, and 5. So let's start with the first one there, negative 1, 1. So that's this point right here. Negative 1, 5. 2, 3, 4, 5. And negative 4, 5. That's going to be right here. So let's look at the sides of this triangle. Okay, so this one is 1, 2, 3 units long. This one is 1, 2, 3, 4 units long. And well, we just did the Pythagorean theorem with the 3 and 4 on the right, around the right angle. And so we could just use this exact same work to determine the third side is going to be 5. And so both of these triangles have 3, 4, and 5 as their side lengths. So actually we don't even need to check the rest of them. It's going to be part A right here.